we're good.
So you're sharing the screen?
Oh, shoot. Okay, 1 second. Can you?
Oh yeah, Ian, I think you have to enable sharing.
Yeah, I allow sharing.
Allow sharing. Okay, good.
Yeah.
So how many people we have online?
Just
One
three.
person. 3 people. Oh, 1 person. Okay, that's good. Well, yeah, welcome again, everyone. So I would like to introduce Adeline Wihardja from Caltech. So this is the first guest that we have from outside Berkeley. We're trying to do some new stuff. But I know Adeline from a friend who's also working in Caltech, but she's another Indonesian. So I was thinking I'm the only Indonesian doing mechanics. So it's a very niche and of course, a lot of people are doing it, but like in this small community, there is even like another subset of small community, which is Indonesian doing mechanics. And Adeline is the other person. And that's the reason why I was thinking, I think it's good. Like if she wanted to come before I leave Berkeley and then so that I can show her around. And I felt like, if you just come by here, like without like meet all you guys, right? And I think it's going to be a little bit a waste. So I think it's good that for her to share a little bit about what she's doing and we can learn together. And Adeline is doing her fifth year Ph.D. right now with Kaushik Bhattacharya. She's doing a lot of works and in experimental and also computational, I guess, and then some image detection stuff, right? So yeah, I'll let Adeline do the talks and yeah, so the floor is yours. Let's give Adeline a hand of applause.
Hi everyone. Thanks for coming to my talk today. I know it's 4 p.m. on a Friday, so I'm gonna keep it short and probably not too technical. All right, so today I'm going to talk about some of the work that I've done on trying to model multifunctional materials and mechanics, right? So my research interest is really in modeling of these multifunctional materials for use in biomedical fields, aerospace industry, and all these different things. And really to be able to leverage and exploit these materials for all these applications, right, we really need to understand their behavior and their underlying physics. Now, unfortunately, a lot of these materials have physics that are usually complex and sometimes multi-scale as well. So the physics is usually not very well understood. So today I'm going to talk about the 2 different ways that I've looked into to try and model and learn the behavior of these materials. So the first is a more traditional approach where we are going to combine experiments and continue modeling to model a class of multifunctional materials called liquid crystal elastomers. And then the second, I'm going to introduce a more data-driven perspective, perhaps where we try to, for materials that are new and emerging materials whose physics is incomplete, we want to try and leverage all the underlying information we can get from our experimental data. And so here we create a new inversion technique called image to constitutive model method that basically allows us to create or to model these materials directly from the raw experimental images. And even when the physics of the material is incomplete. So I'm going to spend some time first talking about the first part of the projects here, where we are going to look into liquid crystal elastomers, right? So liquid crystal elastomers are essentially these soft polymeric materials, okay? And embedded in them is these rigid rod-like molecules, which is also called the pneumatic messages. So these pneumatic messages have what's called a pneumatic order. And what that means is above a certain transition temperature, okay, the pneumatic messages are oriented randomly in space in a disordered manner. So the overall configuration here is isotropic. But then when you cool it down below a certain transition temperature, these messages can rotate and reorient towards a particular direction, a preferential direction, called N here, which is also called our director orientation. And so what's happening here is you have this disordered to ordered phase transition that happens as you cool down with temperature, right? So there's this disordered to ordered phase transition. And as you're cooling it down, the messages rotate and reorient, and they're bringing their polymer chains with them. And so often what you will see is this spontaneous stretch under these phase transition when you cool down these materials. So this large spontaneous stretch, which is also reversible because it's associated with the phase transition, is attractive for several engineering applications. So people have looked into these materials for soft actuation purpose or energy absorption purpose, for example. Okay, so there are generally 2 types of LCE. The first is a monodomain LCE, and the second is what's called polydomain LCE. You can think of it as a single crystal and polycrystal analog, right? So the monodomain is like a single crystal where in a single specimen, you basically have one domain, and all the messages within that domain have one global preferential orientation, right? But with a polydomain LCE, basically you have multiple different domains within a specimen, and each of those domains have their own kind of preferential inflection, basically. And the one thing that I want to highlight here is that polydomain LCE is very easy to make with respect to the monodomain LCE, because for polydomain LCE, you don't need any global alignment thing that you have to tune. And so they're usually very easy to make and also very scalable. And so they make really good engineering materials for the applications that I've showed earlier. So we want to work with these materials, right? And so I'm going to talk about the interesting behavior of these liquid crystal elastomers that people have seen. And in particular, we see that these materials have this spontaneous stretch, right, that happens. And this really stems from the coupling between the liquid crystal or the messages that we see and the rubber elasticity. And in particular, if we look at the mechanical behavior of these materials, okay, they're undergoing this large stretch under very low stress, right? So this is the interesting behavior, which is also called the soft behavior in these materials. And this really comes from the fact that the messages can rotate and orient towards a particular preferential direction. And that direction is not fixed, and it can usually be influenced by external factor. In this case, would be the external loading direction. And so here you see if you are loading a material in the direction parallel to your messaging orientation, you'll get your regular stiff behavior that you would get when you're pulling on a rubber material. But when you're loading it perpendicular to your messaging, for example, you'll get this soft behavior that happens when you have this plateau of stress under very, very large deformation. So people see this as well under X-ray, where they see this angle of direct orientation changing with respect to stretch, right? So the underlying mechanism, however, behind this soft behavior is very, very interesting. So what's happening here is that your messaging can rotate and reorient to lower your energy, which give you lower stresses. Now, at the same time, you also have to satisfy microscopic constraints, microscopic boundary conditions, right? And so they do so simultaneously by forming microstructures. So what's happening in this particular case is you're loading it under uniaxial tensile. You have to also satisfy no-shear boundary condition, right? So they do so by basically forming microstructure, what's called the strike domain formation, where the messaging essentially rotate positively and negatively here to be able to load energy will also satisfy the no-shear boundary condition. Right? So you get this strike domain formation microstructures that we see. So there's this interplay of length scales really, right? Where you have a microstructure formation and evolution. And then macroscopically, what you see is the soft behavior that happens, and also you see a change in your transparency of the material. So if your messages are all aligning in the same way, uniform way, then you get a transparent material. But if they're aligning, they're sort of like misaligned slightly, then you get this opaque material that happens. So these are all the studies that people have done on these monodomain LCE, right? And this change of opacity is a pretty good indication that you can see with your naked eye that there is this microstructure evolution and formation that happens in these materials. Okay, so people also kind of study this material for polydomain LCE as well. And thankfully for polydomain LCE, you also see this behavior, right? So you see the material changing opacity from opaque to transparent, indicating that there's some messaging orientation and realignment that happens with respect to the loading direction. Okay, and this change is reversible when you heat the material as well. So that's sort of like the idea. And so again, the polydomain LCE are these LCE that is easy to make, right? So they make really good engineering materials for these applications that we want to leverage them for. And so what we've been working on is trying to get a high fidelity engineering scale model for these polydomains, right? In particular, we have some requirement that we want our model to satisfy. So first of all, we see that these materials have microstructure formation and evolution, that is important that we want to really take into account. So we better be able to incorporate some of these micromechanics, right? And then second of all, we also want to have this material under complex real-world scenarios, so it should be able to capture multi-axial loading. And then last thing is we want to kind of be able to leverage this material under energy absorption or impact absorption applications. So we want to also incorporate some rate sensitivity and rate dependent coupling of the liquid crystal and the viscoelasticity as well. Okay, so for the next couple of minutes, I'm going to just spend some time talking about the rate independent part of the model, where we're not considering high strain rate behavior of these materials, right? So just fully rate independent model. Okay, so we're going to look specifically to model these polydomain LCE, right? And so in a polydomain LCE, we really have this separation of length scales, where in the specimen in the macro scale here, we have the sample, and then in the meso scale, we have a collection of our domains, the domain patterns, and each of those domains have a preferential direction of the messages along some direction, right? So this is the monodomain on micro scale, basically. So we are going to try and build our model, and we're going to consider the smallest building block here, which is the monodomain case. So this is the material in the micro scale. We're just considering the domain scale. And the theory for this is very well developed, right? It's called the classical theory of LCE. So people have developed this back in the 90s. So I'm going to present just a big picture of that, because we're going to build on that model for our polydomain LCE model. Okay, so the classical theory of LCE for monodomain is actually the whole idea here is that the material essentially has a polymer backbone, right? So we're going to consider the simplest energy density form, which is the new Hookean energy density for our rubber materials, right? Now, the important thing here that I want to highlight is that this energy has exactly one ground state, one energy minimizing state. And so this is when the material is undeformed, right? So now we also remember, however, that we're cross-linking this material with the pneumatic messages, right? And the pneumatic messages have a preferential direction along this particular direction N. And so these three people, Glenn, Trenchif, and Water, take into account this anisotropy via this L tensor here, right? So this L tensor basically is the anisotropy tensor that takes into account this messaging preferential direction of the messaging. Now, this L tensor also encodes all the energy minimizing state. And in particular, if we look closely as to what this is, now we have new energy minimizing states that's different from before. Now, the new ground state will be some rotation of this particular base tensor, which is a uniaxial stretch state, right? And if we remember, we've seen this before, this corresponds to the spontaneous stretch state under these phase transition, right? So this is a uniaxial stretch state, and this gives you basically the energy minimizing state where you have this low stress behavior. Now, we remember that this particular direction is, it can be influenced by external factor, right? In particular, it is unique up to some rotation, okay? So basically what that means is that now you have a degeneracy of energy minimizing state. You have multiple energy minimizing state because the material can rotate and reorient towards any particular external loading direction that you're subjecting it to. So now we no longer have just one energy minimizing state, we have a multitude of these energy minimizing states, right? And so this is captured with this L tensor here. So again, we have a degeneracy of the energy minimizing state. Okay, so that's the classical theory. Now we're going to build on that classical theory to kind of try and model our polydomain LCE, right? So we consider an RVE in the mesoscale here, and we're going to basically borrow concepts from the classical model, where now we postulate in the mesoscale, we postulate in the mesoscale that there also is a spontaneous deformation tensor. So this is our ground state, right? Where we postulate that there exists spontaneous deformation tensor G here. So this is analogous to the classical model, the L tensor here. Right, so this is spontaneous deformation tensor is the energy minimizing state, right? And so it will be some rotation, again, same as before, right? With respect to the base tensor G naught here. The base tensor here now is parameterized with two variables, lambda and delta. So we can derive and show from microstructural consideration and statistical argument that our lambda and delta here is going to be physically linked to some physical property in the micro scale, right? So in particular, lambda and delta describes roughly in a coarse grained manner the spontaneous deformation in the mesoscale, and you can derive from statistical argument and kind of physically link lambda basically to the alignment of all the messages along the principal direction of the RVE, and delta to the alignment of all the messages along the outer plane direction of the RVE. So I won't show that here because that's a little too much detail, but happy to talk about it after. Now, of course, the mesoscale model here has to respect the microscale limit, right? So we have some limitations as to what lambda and delta values can take, and this is bounded into some region A following the microscale limit. So now you have to specify the energy density, the strain energy density function. And so to do that, we basically try and draw from some experimental knowledge that we have seen. So this is people in Japan doing really careful biaxial experiments on these rubber materials. So on LCE as well as on conventional rubber, right? So they're imposing this biaxial stretch, two different biaxial stretch on this material. And in a regular rubber, usually when you do two different biaxial stretching, you would get two different principal stress in that's different, that's unequal, right, in the two direction. But what's interesting is that for this polydomain LCE, you can impose two different principal strain, but you end up getting the same kind of like two principal stresses up until some value. And so what that means here is that in the polydomain LCE, you have a mechanism to negate in-plane shear stress, right? So you have the two principal stresses are the same, so basically you didn't have no shear stress. So there's a mechanism here that can negate this shear stress. And so they also kind of look at this material with X-ray imaging and see indeed that there is a evolution in the messages of these materials that negates the in-plane shear stress. So, okay, from these experimental insight, we basically conclude and postulate that these two variables, lambda and delta, these two parameters, is going to be enough to be able to capture the macroscopic quantity of interest here, which is our macroscopic stress. So now we're going to borrow concepts from internal variable theory and basically say, okay, lambda and delta, which is linked to our spontaneous deformation in the mesoscale, is going to be our two internal variables. Okay, and the internal variables basically is going to account for the microstructures formation and evolution in a coarse-grained manner to be able to predict our macroscopic stress, right? So that's basically the whole idea. Basically, we're claiming, okay, if we know the state of our internal variables at that particular space and time, we know enough information about the history and about the microstructure of these materials to be able to predict the stress. And so now we can kind of postulate the strain energy density for these materials, right? So it will be some elastic energy with respect to the new ground state, which is the G tensor here, the spontaneous deformation state that is furnished by these two internal variables, lambda and delta. So here's our specific form, but the specific form of the energy doesn't really matter. Here we're just really using the internal variable lambda and delta, which is again the spontaneous deformation in the mesoscale, to account for these micromechanics in a coarse-grained manner to be able to give us our macroscopic stress. So the evolution of the internal variables encapsulate our microstructural evolution as well. And here we just assume a very simple form of a quadratic dissipation potential. And stationarity of the energy density and the dissipation gives us the following. Evolution law is the simplest evolution law that you can get.
Adeline,
Yeah.
ask a question about you have the WR there.
Yeah.
Is this going to force lambda and delta to sit inside this little?
Correct. Yes. The tiny region A that you see there.
Yeah. A,
Yes.
Sorry.
Yeah, that region.
Okay, so it takes care of all of A or just some parts of it?
So it takes care of particularly this part of it.
Yeah.
Yeah.
Okay, but not the other two sides.
Not the other two sides,
Okay.
no. Yeah. The other two sides we just kind of constrain it with a 4 point. Yeah. We numerically implement them all. All right, that is basically what I have so far on the rate independent part of the model for these polydomain LCE. And so we see that we kind of try and capture the microstructure formation and evolution in a coarse-grained manner with the two internal variables that we've talked about before. And we draw some insights from multi-axial loading experiments. And now we want to consider multiphasic or temperature-dependent loading. And so here in the lab, we basically did that by creating this new temperature-controlled setup for our LCE. Here, basically, we just have a regular tensile setup, and then we enclose it under a temperature chamber in a lab to be able to give us a full set of data for the temperature-dependent behavior, as well as strain rate-dependent behavior for quite low strain rate, right? So quasi-static strain rates. But this gives us experimental data that is temperature-dependent, and we are able to kind of compare the experiments in the model and see that they roughly kind of match with each other. And this is the work that I have done also with Alice, which is an undergrad in our lab. So now I'm going to kind of move on and try and look at this behavior under high strain rate loading, right? Because we're motivated by the impact absorption applications for these materials. So we want to really be able to capture a rate-dependent coupling between the liquid crystals and the rubber elasticity. Okay, so to do that, we borrow theory from large deformation viscoelasticity. It was actually developed by Sanjay here. So we borrow theory that he developed, and we consider the following rheological model for our LCE, where we have the two branches, right? So the left branch is also called the equilibrium branch. So this follows exactly the same model as before, right? So this is the true equilibrium, no strain rate dependence. At time infinity, basically, where this will take into account our pneumatic elasticity and our liquid crystals. So this is the where we take into account the microscale with the internal variables as before. And then on the right branch here, we have the also called the non-equilibrium branch, right? So this will take into account the viscoelasticity of our rubber materials. And we assume the following decomposition of our deformation gradient. Okay, so now we're going to invoke the continuum mechanics recipe for these liquid crystals. We assume again the following decomposition of our deformation gradient, and then we have our regular balance laws, right? So this is typical balance law, and we assume the following, we postulate the following dependence of our conservative form, where now we have the two internal variables in the equilibrium case, and we also have an additional internal variable because we have to take into account these rate sensitivity effect. And so what this physically means is the elastic instantaneous response of the polymer with the load materials, right? So we can combine the two energy with the conservative form, and this lands us to our dissipation inequality, right? And then in arguing as Coleman and Knoll, basically any thermoelastic processes, we basically can we get relationship of our elastic stress in particular and entropy as well as heat flow. Now we have these following terms in our dissipation potential now that has to be satisfied, right? So we're a little stuck. We need some more model for all these internal variable, if you see. And so what we can do here is we can see this as a product, right, of our energetic terms as well as our rate terms, right? So this is like your friction law. And basically what you can do is now we can identify these two as conjugate pairings, where the energetic term is your thermodynamic driving force for your internal variables here. And so this leads us to be able to postulate an evolution law for the internal variables that we picked here, these three internal variables, right? Where the internal variables now is going to be dependent on the conjugate thermodynamic driving forces, right? From our dissipation inequality here. Okay. So now we can specify a specific form for our energy density, where we have, again, the two energy addition energy, right? So this is the same energy as before, which is the equilibrium energy that we've seen earlier. So this is exactly the same thing, where we have some elastic energy with respect to the spontaneous deformation state or the energy minimizing state. And then you can add to that the non-equilibrium energy, so to speak, of this elastic response of the rubber, and we just assume a very simple Newtonian form of this energy. And oopsies, we have to ensure basically for this energy that at time infinity or at true equilibrium, basically, the energy, the term from this energy goes to zero, as well as stress associated with this additional energy also goes to zero. I somehow deleted my slide that, okay, we also have to specify the dissipation potential for our internal variables, lambda, delta, and Fe here. And we just assume a quadratic dissipation potential. And that leads you to the same linear form where your evolution of your internal variable depends on the driving force in a linear fashion. Sorry, I deleted that slide, so don't have a slide for that, but that's essentially the whole idea. Okay, so now that we have our model, right, we really want to study this material experimentally. And in particular, we want to try and get a sense of the behavior of this material under high strain rate condition, because we want to capture that rate-dependent coupling of the liquid crystal and the rubber elasticity. So now we turn into experiments on this polydomain LCD, right? And when we actually start looking into the high strain rate behavior of this liquid crystal, it was actually hard because the high strain rate behavior is not very well characterized for these materials. And I think the reason for that is because there does not exist a established experimental setup for these soft material systems that can probe the behavior under the deformation regime we're interested in. In particular, we're interested in the deformation regime of high strain rate and also pretty large strain of these materials, right? So one can think of using an instron, for example, as this is your typical MTS or instron hydraulic machine. Now you can probe high strain behavior, but usually it's pretty low strain rate. And then you can go to the other end and do some split Hopkinson experiments on these material. And this gives you large strain rate. You can probe the large strain rate behavior, but the strain that you get because of the nature of these experiments is usually pretty low, right? And we're interested in probing deformation for this material under large strain rate and also large strain, because the soft behavior that we get is really the soft mode under very large strain, right? So we want to capture that here. So to do that, we basically created a new tensile drop tower setup in our lab. And this allows us to kind of probe the behavior of this material under high strain and high strain rate. It's okay. I don't know how to play the video, but there's a video here. Yeah. There we go. But this is basically the projectile that you see that we drop under a certain height here. So this entire thing is like the drop height is about 2 meters height. And so once the projectile drop, it will basically pull on the material. So you can kind of control the strain rate that you get depending on your drop height here. Okay, and then we also test the behavior of this material under compression with a split Hopkinson pressure bar setup that we have in our lab. So let's see if I can play this thing. But yeah, so there's a split Hopkinson setup. Okay, so here is basically the results. So these multiple curve is the experimental result, and the dotted line is the simulation result. The experimental data is like slightly noisy, but what we can see here, right, is that this is under low strain rate, and you get stiffening as you get higher and higher strain rate. So this makes sense, right? You get this highest strain rate stiffening basically in these materials. Another thing that is important to note here is that the soft behavior that you see under this quasi-static regime is very much suppressed when you test this material at high strain rate. Now, this material also, a disclaimer, this material has, I think, about 40% crosslink. So the behavior that you see is probably mostly dominated by the rubber behavior. So we can get more physical insight as to what's happening in this material when we look at the evolution of the internal variable. And in particular, our internal variable can be physically linked to some kind of physical quantity, right? So lambda here is sort of like an indication of our spontaneous deformation, right? Because that's descriptor of the spontaneous stretch in the mesoscale. And you see as we go higher and higher strain rate, basically lambda, which is our spontaneous stretch here, is getting more and more suppressed, right? And then FE here, which is elastic instantaneous response, when we at low strain rate, basically the polymer is allowed to relax completely. But then when you go higher and higher strain rate, basically you get this larger and larger elastic resistance in the polymer when we first load it. And so this leads to, this leads to basically stiffening effect of this strain rate stiffening that you see. And then the same trend you can also basically see in the compression as well. And then, yeah, that's basically the same trend. So I won't go into too much detail there. Okay, so that's essentially the model that we kind of have been developing in the lab. But really, we try to incorporate some microstructure physics in this model. We also try and capture from multi-axial experiments, and we also try and really capture this rate-dependent coupling of the liquid crystals and the rubber losses. So now this model is developed in an engineering scale where you can then use it and implement it in your favorite finite element simulation software. So here, some people actually took it. Neda here, which is now at USC, she took these kind of model and put it into a finite element. I think she's using Abacus, where she looked into some creasing instability, some adhesion, some Hertz contact, as well as some torsion instability behavior of this material. Okay, so I am going to kind of move on to the second part of the talk, but I'm going to summarize what we've done so far, right? So we start with the underlying physics of these materials, and this allowed some people to develop classical model for these materials, right? So this is the classical model that London, Trentiev, and Warner has developed. And usually with these materials, we then want to use it for real applications. So we would supplement these with some, knowledge about maybe the microstructures, knowledge about experiments at high strain rate, or some other experiments, biaxial experiments, for example, in our case. We can also integrate some lower scale information about the physics that we know from microscale imaging, for example, X-ray and whatnot, that gives us some idea about the microstructure evolution, for example. And this leads us to be able to create a more high fidelity model of this material that is based on physics, right? Now, this is great because for liquid crystal, this domain knowledge has existed for the past 30 years, for example, right? Because this material has been characterized for quite some time. But now it's possible to have new emerging materials, right? And for new emerging materials, you don't necessarily have access to all these domain knowledge, right? And so this begs the question for these new materials whose physics is incomplete, right? Now we ask the question, once we run an experiment on these materials, how can we really leverage all the underlying information and all the underlying data from the experiments that we just run to be able to inform the model that we want to get for these materials, right? So this leads us to the second part of the project where we try and create a new inversion technique called image to consider model, where we can get basically considered relations directly from raw images because we really want to leverage all the underlying data in that raw experimental images, right? Okay, so in general, it is a little hard to try and get considered relations directly from experimental data. And so the reason for that is our constitutive law is usually a relationship between the stress and the strain, right? So the stress and strain is not directly measurable in an experiment. You never directly measure that. So what people have done traditionally, right, and so this is what Rivlin and Saunders did back in the 50s to model their rubber materials, is they impose a state of uniform strain in the material. So they do these very, very careful experiments to get a state of uniform strain in the materials. And by the measurement of these boundary forces, okay, you can get the stress associated with that strain. So one experiment basically gives you one stress and strain data point, right? So this is actually rather a low throughput because you have to repeat these experiments multiple times. And another thing is that when we then use the model to real complex scenario, most of the time we will have multi-axial loading conditions, right? And so the model developed with these uniform stress and strain might not be sufficient to characterize the material under a complex multi-axial loading condition for real-world applications. So of course, people have kind of moved away from this approach. Now with the development of optics and electronics, you have a potential to get full field images. And with that, that gives you potential to get full field data, right? And that means you can leverage basically non-uniform strain in your material, right? So non-uniform strain here, for example, if you have crack or holes, you have complex states in the material that can give you more information to then be able to back out a model from these non-uniform strain, right? Because you're sampling basically multiple different strain states in the material at once within a single experiment. So that gives you more data for your model. But of course, there's no free lunch. Now you have to solve a more complex inverse problem. And so the way people solve these complex inverse problem now is they usually divide it into two steps, right? So the first thing that they do is they try to infer displacements from their images. And so this is also called the DIC problem. And then after getting a full field displacement, you can get your material parameters and basically get your model. So there exist some limitations with this approach. So again, the first step here is usually called the digital image correlation, if you've heard of that or kind of played with that. And digital image correlation as a purely kinematic problem is an ill-posed problem, right? So the inversion here that you're doing is usually independent of the physics of the problem. And so that leads to an ill-posed problem, and that usually leads to information loss when you're going from backing out your displacement from the images. And then the second step is usually done with visual fields method, or FMU here. And limitations in the analysis part here also leads you to be able to only do idealized idealized experiments, so things like uniaxial tensor, biaxial experiments that are rather idealized geometry. And so this leads you to also sparse data, because once you have complex states, these methods tend to fail, or it has basically large error when you have holes or when you have fracture in the material. And then of course you run into issues with any nested optimization technique where you have sensitivity mismatch between the step 1 and step 2, or you can also have error accumulation through this entire process, right? Okay, so now we're going to basically propose a method where we can learn considered relations, considered model directly from the raw experimental images as a one-step method. So we're not considering these two-step anymore. And in doing so, we're trying to basically avoid all the limitations that we've seen here that is associated with these two-step approach that traditionally people are doing. Okay, so before moving into talking about this method, I'm going to talk about digital image correlation first. So for people who are not familiar, digital image correlation is basically an inverse problem. And the problem really is you have your sample, you have your material, and you usually put some textured or speckled pattern into your material, right? So these are speckled materials. And as you're then deforming this material, your speckle pattern will deform with the material. And as you're doing that, you're basically taking a series of snapshots, a series of images, right? So you end up with these series of images of your speckle pattern deforming. And the DIC problem really is, assuming your grayscale or your speckle pattern here convex with the deformation, we really are trying to minimize the difference between the deformed speckles with respect to the undeformed speckles over all possible solution field U here. So U is our displacement field, and we're really trying to maximize the correlation between the two eventually, right? Now, this is a typical classical optimal transport problem, and it is well known here that the minimizers may not exist, or if you have minimizing sequence, they may not converge. So DIC here is an ill-posed problem because of these reasons. And in practice, people still solve this problem, right? So people still solve the DIC problem, and they do so by regularizing it. And what that means is they assume a finite dimensional ansatz on their displacement field U here. So in practice, two are common. So the first is what's called the local ansatz, and the second is the global ansatz. So this local ansatz, basically what the idea here is that you take your images and you divide it into multiple subsets, into smaller and smaller subsets. you're basically saying, okay, my deformation is going to be affine within that subset. And then you're basically tracking the center of that subset, the displacement at the center of the subset here. And then the rest of the subset is basically affine deformation. And then for the global DIC, basically you're saying, okay, my displacement field is going to be a linear span of all these global basis functions. So there's problems. The local DIC here, you can see that the deformation field is actually not going to be compatible. It's not globally compatible. So people takes care of this by looking into the global DIC, which gives you compatible fields. But in both of these approach, right, you have these, and here is also the regularization parameter. There is no notion of convergence as you keep increasing your subset size, which is n here, or as you keep increasing the number of basis functions that you're using. So there's no notion of conversion and there's no notion of error in these methods, right? And in fact, when you actually go ahead and do experiments with DIC, what you often see is that when you have a complex state in your material, when you have holes near the boundaries, near the edges, okay, your displacement solution that you get from this method tends to be really, really sensitive to these regularization parameters, right? So if you vary your subset size a little bit, if you vary how much basis functions you're using, you get a different displacement solution, and it gets more and more sensitive when you have complex states in the material. And that is not really good, because complex states of the material is when you're sampling a non-uniform strain states in your material, right? So that's when you usually would get most information to back out a model from. Okay, so now I'm going to talk about the integrated approach, where we basically bypass this ill-posedness of DIC, because we're bypassing that step altogether, where we directly go from the images to the displacement. And we're going to use the laws of physics, the physical phenomena, the PDE of the problem, to regularize our displacement solution. Okay, so here's how the integrated approach works, right? So usually in an experiment, we have our direct measurables. And so our direct measurables is the series of our raw images that we get. Here I denoted as G. We also have the boundary force. Usually we will measure kind of like the force at the boundary here, right, with our experimental setup. Now you can emulate the experiments in our simulation, right? We can impose the exact same boundary conditions. You also know the physical phenomena that you're subjecting your material to. So you know your governing PDE here is just a typical equilibrium PDE. You also have to supplement our simulation with a conservative law. So of course, this is what we are trying to get. We're trying to get our model. So this does not have to be the exact conservative law. It just has to be parameterized with some parameters at P here. Okay, so now we have all our information to do our simulation. So we can run your simulation and you can get your displacement field as well as your simulated force at the boundary, right? So our raw data is still our raw images. So what we can do here is we can warp the displacement, the simulated displacement, with the speckle pattern that we started off in our experiments, right? So we can warp this, warp the displacement with the experimental speckle pattern. Right, so you can get now basically a series of your simulated images. So now we can compare your simulated images with your experimental images, right? So here this is our objective. It's an optimization problem. So our objective will be the difference between our simulated and experimental images, as well as simulated and experimental forces, right? So really the important thing here that I want to highlight is, if you notice, the displacement field that we get here already satisfies our governing PDE, right? So this displacement field already satisfies equilibrium and compatibility. And so this is different than the current established approach, because we're in trying to minimize this objective, we're looking over all possible material parameters P here, while already constraining ourselves, restricting ourselves to the displacement field that already comes from our P. Right, so the displacement field here already has to satisfy our governing PDE. Okay, so here's how the problem works, right? So we're posing this as an optimization problem. This is our objective, the difference between the simulated and experimental images and forces. And we are going to pose this as a PDE constraint optimization, where this is our PDE and it's just a weak form of our equilibrium equation. Okay. So we are going to solve for this with a gradient-based PDE constraint optimization technique. And in any gradient-based approach, you will run into issues because when you try and get sensitivity to update your material parameters, right, to get your model, to get your best material parameters, you need this thing right here. And this is generally difficult to compute. If you think about this physically, what this means is a sensitivity of your solution field, of your displacement field, which is a solution to our PDE, right, with respect to our material parameters that we're looking for. So for a lot of materials, this is usually difficult to compute and difficult to store, especially if you have a hyperparameterized model in some sense. This is difficult to compute. And so to try and compare it with established method, usually people do FMU or virtual fields method, right, for these kind of for these inverse modeling approach. And with FMU or virtual fields method, they try and always get these terms, usually with finite differentiation or some other kind of method. But you still have to compute these terms, and usually in these methods, they're not scalable, as in the more material parameters that you get, it's harder and harder to try and get an accurate solution. So these methods tend to struggle with these calculations right here. So in our approach, we basically want to try and eliminate a calculation of this because this is difficult to compute. And in particular, what we did is we introduced an auxiliary field. We introduced what's called an adjoint variable to try and make a special choice to eliminate calculation of these terms for our sensitivity update. In particular, we're going to claim, here's our sensitivity. Okay, we don't have the difficult term anymore, the dy/dp term. Here's our sensitivity. If and only if our adjoint variable, phi here, which is the auxiliary variable we introduced, satisfy the following adjoint PDE. Right. So basically, eliminate calculation of that term by introducing a whole other PDE that we have to solve. Now I'm going to spend some detail to talk about this PDE. So this is our adjoint variable. The forcing terms of our adjoint PDE comes from the objective, right? So this is the image mismatch term, and this is the force mismatch term. So this makes sense. Basically, the objective will basically drive our adjoint PDE, our adjoint variable. And in particular, if we look closely and kind of like compare the adjoint PDE and the forward PDE that we have, the adjoint PDE is a linearization of the forward PDE. So this is actually usually easier to solve than the forward PDE. And then second thing is I haven't made any claim about how many material parameters I'm trying to solve, right? And so this is the beauty of this method, the adjoint method, is that regardless of the number of material parameters that you have, you only have to solve one adjoint PDE. So you can get the sensitivity for all your material parameters by just solving this one adjoint PDE in the final. And then this, of course, you have to satisfy this over all possible perturbations of your displacement field. Okay, so again, the good thing about the adjoint method is that it's a linearization of your forward PDE. So we're already solving for the forward PDE anyways in our final element. And the adjoint PDE is easier to solve. And then second of all, it's cost independent with respect to the number of material parameters. So it takes care of this difficulty that established method like FMU usually run across for difficulty, right? Okay, and so here's how the algorithm works. We usually have our series of images from our experiments, and then we have to input some parameterized form of the model. And then we basically initialize our parameters, and then we run our forward and our adjoint problem in our final element, right? And then we obtain our sensitivity and keep updating until basically convergence until we get the best material parameters. Okay, so for the rest of the talk, now I'm going to just spend a little bit of detail talking about some examples. So here we look into rubber materials. So this is finite deformation, elasticity. And we first try it with synthetic data. We try our method with synthetic data because if it doesn't work with synthetic data, it will never work. So we're going to try it first with synthetic data, okay? So here we use a Newhookian model. So basically, this is a ground truth model, right? Where we have two unknowns, the shear and the bulk modulus. And running the forward model, we can get raw images as well as forces. So basically, these two will be our data that we input into our algorithm that we see earlier, right? So of course, the simplest case is where we assume we're just not going to do any model selection. We're going to assume the same model form, right, with our synthetic data, and we're just going to look at whether we can recover the two unknowns, the two shear modulus and bulk modulus. And indeed, we see that we kind of recover the same, roughly the same shear and bulk modulus. Yeah. So that's kind of cheating because we're basically saying, okay, well, we're going to assume the same model form, right? But now really it's in real data, in real models, right? We usually don't know what our model form is, and that's usually part of the equation itself. So we know we're working with rubber, so we're going to use a different initial guess for the model form, where we now consider a Mooney-Rivlin model form that's different from the synthetic data. And we run the algorithm again, and we basically recover some parameters. Now we have these two different models, right? The synthetic model, which is our ground truth model, and the recovered conservative model from our algorithm. But really, the specific form of the model doesn't really matter as long as we're able to capture the exact same material behavior, right? So that's what we want. So what we did here is we run a validation with an independent test, independent different specimen geometry. And we compare the boundary forces, and they kind of match with each other. We also compare basically the stress, flow field stress response, right? And we characterize the L2 stress, the L2 difference of the synthetic and the recovered model for the stress field, and the errors are quite negligible for the deformation regime that we're interested in, of course, right? So we conclude that the algorithm can recover a conservative relation without knowledge of the specific model form. Now, and then the real test really is when we're trying to work experimental data. So here we try and get some real experimental data. So I went on McMaster and get this natural rubber. And this is real speckle that I kind of have to go ahead and actually do the speckling myself with some Sharpie. So here's, we kind of pull on this material, right? And so this is the one image and another image. Basically, this is our data that we then input for our algorithm. And then we assume the following parameters conservative, and we can run the algorithm that we see, and this leads you to some learned parameters for our conservative form. So now we can recover, basically this is our model, right, from the learning process from the experimental data. So again, with the experimental data with real rubber now, we actually don't know what our model is. We have no idea of the ground truth of the model. So what we can do here is we can compare our method with the current method that exists out there, which is DIC, because that's the only method that exists, right? So what we did here is we run the validation on an independent test specimen with a different geometry. You can speckle it with some spray paint and then run the DIC problem. You can also run the simulation with the learned conservative law that we've gotten from the inversion, right? So, okay, we use Vic2D from correlated solutions to perform our DIC. And here's the quantitative difference between the two. So the blue curve here is from Vic2D data, and the red curve here is from our algorithm. And we see that quantitatively they kind of match with each other, the strain fields as well as the force. And then you also see here in the right part, this is a more qualitative, qualitatively kind of see the difference between Vic2D data. So this is our experimental data on the left at various different strain. And this is the model that we run from our inversion algorithm. Right, and so qualitatively, they also kind of match with each other. And then I think I have here a video of basically the two, okay, sorry, the two things side by side. Let me see if I can kind of run that back. Probably not, but okay, there we go. Some video of so this is the real experiment that we analyzed with the DIC, the Vic2D software, and this is our simulated data. Okay, but in general, we kind of conclude that we can recover conservative relations from these experimental images, from real experimental images. So currently now we're working, so this is rubber elasticity, it's fairly simple material, fairly simple model. And so we're trying to extend this method as well to try and recover conservative models for material with history, for example, plasticity, macroplasticity, as well as for materials with some hyperparameterized model where we don't know the exact physics of the material. So that's what we're working on now. Okay, but what I want to particularly highlight here, right? So with experimental data, with VIC-2D that we analyze with GIC, usually they tend to be quite sensitive, and this is what I was talking about earlier, right? So near boundaries and near holes, usually they tend to be really sensitive. There's displacement field that you get tend to be sensitive to the subset size or these regularization parameters that you use. But because of the nature of our method, we're still able to kind of recover the behavior at these complex states. And so this allows us to potentially leverage complex states to then use these states to inform our model recovery of these materials. Okay, so in general, I'm just going to summarize that our integrated method can basically learn consider relations from raw images in a one-step method, directly going from images to finding these parameters. Right, and in doing so, we alleviate errors from current methods with GIC and FMU. And also the cost is independent with respect to the material parameters, so it's pretty scalable. And then it's also amenable to complex geometry and loading cases. And we are going to extend this to non-classical models, right? Okay, so that's overall kind of what I have done during my PhD. And so in general, right, this is the big picture where we try and really do some model discovery in mechanics where we can try and use a traditional method of a combination of both experiments and modeling to try and get models for these materials. One can also look at it from a more data-driven approach if you have a new material or emerging material where you have incomplete knowledge of the physics to try and leverage all the underlying information from the fine scale features of your raw data, of your images here, try and get the model. So this allows us to create models for these materials. And so the next question that I think is interesting is, okay, once we get a model for these materials, how can we leverage the model, the physics of these materials that we know about from this model to try and do optimal experimental design, right? So this is a difficult problem where usually people try and use simple geometry to do experiments, but we can leverage complex geometry and complex loading to sample non-uniform strain states in your material to give you enough to sample enough of your strain states in your material to give you enough data within a single experiment, right? So the image reconstitutive model method that I've developed here, you can previously, what I've shown here is a deterministic setting, right? Where we optimize, where we try and pose it as an optimization problem. Now, you can also look at it from a Bayesian perspective, and this allows you to get some uncertainty of the inferred model. In particular, you can get some quantitative expression of your model uncertainty, of your inferred model uncertainty, and this allows you to basically do quantitative optimal experimental design, where now you ask, okay, what's the best topology or what's the best Western geometry that can basically minimize the uncertainty in the model that we can then infer. So now we're working on trying to do this optimal experimental design with topology optimization methods to basically try and get the density field here that can minimize the uncertainty of the model that we will infer before seeing any real experimental data. So that's essentially the whole idea of what I'm currently working on. And I think my outlook for the future is I am interested in a strong integration of these modeling and experimentations, right, for this multifunctional material, where we want to really enhance our models and leverage all the underlying information from the raw data to be able to inform our model. And this allows us to get a higher fidelity model. Now, after getting these models, we can then use the physics of these models as we refine these models to then pose the optimal experimental design question, where we can get higher and higher fidelity experimentations given these physics of the model. So yeah, that's essentially what I have been working on and what I'm currently working on and what I'm interested in to work on. And here's just some of the collaborations of the people I've worked with at Caltech and other schools, as well as funding sources. But yeah, thank you for coming to the seminar. Thank you for hosting me, and I really appreciate it.
I have a couple of questions for the first one.
Hmm.
So for the macro scale, you said these are the internal variables, this lambda and delta.
Yeah.
How do you, like, maybe I missed it, like, how do you do the scale transition from the micro to the macro? How do you determine?
Okay, yeah. So this we typically use a statistical averaging where basically we take into account all the messages within the specimen and then we do some averaging of that. So there's more detail in the paper. But essentially the averaging is done within the RDE, right? And so then it will give you some idea of the coarse grain of all the messages within that domain. And then we're basically just saying, okay, looking at the order tensor that we've seen in the monodomain scale, we can postulate the same order tensor in the mesoscale as well. But now we're not considering, because in the monodomain scale, you're considering uniaxial stretch state as your in your order tensor. But here, because we're coarse graining it, we're not assuming that relationship anymore, right? So lambda and delta is just two parameters that we use. And then you have incompressibility constraint as well there. But it's from statistical averaging. You can look at that for more detail, I guess, in the paper, which, yeah, I can also show you after.
But you don't use any, let's say, energy or power equivalent kind of thing, what we usually do for homogenization.
No.
So how do you get the initial values of all these tensors? For, I mean, like, say there is a specimen that you have, right? And all of them have different directors. Like, how do you get the coarse graining average of all these initial values and if, for example, if I'm just trying to read the two sort of like field projects that you were doing. If you want to get like that, how do you see that it can be linked? Like, what is the initial states of the dark?
So because we're working with polydomain LCE, we know that originally in the uniform state, they're in the isotropic configuration.
Oh, there. That's
Yeah. So we're just going, okay, well, on average, it's a crystal processing, right? They're like all in a different direction, but we're considering the averaging of it. And
always.
isotropic configuration.
And then as you pull those
Yeah.
to be honest.
Right. And so that change from isotropic configuration is captured by lambda and delta on average.
Very fascinating presentation. I wonder how this material, this LCE material will behave. For example, if the whole basement is cooling down from a very high temperature to a very low temperature, so the structure will transit from anisotropic structure to isotropic structure. So I feel like the stiffness for isotropic here is higher. So do you expect there will be a fracture in the middle of it because of the incompatibility of these two states during the cooling down procedure?
Oh, we actually never really assume that. We never assume any fracture during the cooling down state.
Yeah, I just wonder if.
But I think you can reform. I mean, if the stiffness changed, then you gotta like shorten.
Yeah, because I thought you fix both upper and lower bound of the material.
Then when you cool down, this is gonna go.
The wheel on the bottom.
Okay. But I was wondering if I just fix the top and bottom and then I write
Oh yeah, then you probably would get.
You have like, yeah.
If you combine it completely, then probably yes.
Yeah.
You have to keep some detail because the transition wants it to change shape, and if you don't allow change,
I think this mechanism can be a great switch mechanism for the engineering application because as the temperature drops down, so the whole material just break, and then it's kind of like switch this mechanism. Oh, I have another question about the joint PDE.
Yeah.
The second on page 6.
Okay. It's transition. It's transition. Okay, you want this?
I wonder if I'm not sure if I understand the joint PDE correctly. So you said you introduce additional. My understanding is like you introduce an additional variable.
Yes.
And then you do integration by part so that you can eliminate partial y, partial p that part. See that?
No, not quite. So you can see this from the previous structure, right? So we basically we're going to collect terms that has these terms right here. And then if you see this part, right, this becomes in our adjoint PDE. So basically we're choosing for we're introducing an additional variable where we basically did this additional,
Can you remind us again why it is difficult to get this deep? Because if you have like say two variables like what you did just now, like with bulk modules. So for every displacement field, you will have this sort of like relation dydp for every. So for example, for every displacement field that you can translate. So just one problem.
Yeah, so when you run your for problem, you only have one displacement field corresponding to that for problem. The difficult thing is that if you have a large number of chain parameters,
Oh yeah. Okay.
right? So and then also, right? So you basically in the file element, you usually store your displacement field. So this is like full field displacement field that you store. Now we have two material parameters, you store two more of these. So you're storing one displacement field and then you're storing all of that. So that is usually difficult to store. And if you have like crystal processing.
But if you can pay for this, easier.
Well, I think it's easier to still do adjoint.
So
Yeah, because with adjoint you really don't store those. But okay, so the thing here is that what you notice is we collect all these terms, right? And then these terms become terms in our adjoint PDE.
but that's an extra PDE you solve.
Yeah, that's an extra PDE you solve. But you're already solving for your forward PDE, right? So you and then this is usually really easy to solve as well in a finite element. This is a linear PDE if you notice, right? So this is linearized version of that. This actually has the same stiffness matrix.
That's right. So you can
reuse it exactly. So this is very easy to solve. You just have to. It's just the same exact PDE, just with a different forcing.
have to solve subsequent. I was just thinking subsequent after
right after you solve.
Right after you solve that, you solve that.
Yes.
So what's the phi, gradient of phi?
Phi here is our adjoint PDE. Yeah. So basically the dydp terms becomes like these terms, and then we're solving for this additional variable phi here. And then by solving for this additional variable phi, I think the physical meaning of it is that we're choosing dydp such that these terms basically goes to 0. So all these terms goes to 0, and if those terms goes to 0, then you can shrink, your sensitivity becomes shorter, and then all these terms, that's why all these terms you're setting it to 0, right? So if this contribution is 0, then this large thing, basically this term is eliminated, this term is eliminated, this term is eliminated, you're just left with the other terms, which then you can update for your sensitivity quite easily.
I have a follow-up question. So right now, like for example, this stuff that you're working on is like constant, 2 different constant or 5 different constant for many different, right? Or 4 different constant for that. But what happens if you have like a material parameters which is actually a functions of others, or like, you know, set pressure dependent or like temperature dependent, like all this stuff. How do you actually can the joint model guarantee a solutions for those type of like non-linear?
You can always form adjoint.
You can all, but you have to reform the.
You have to reformulate, yeah.
That's
So for different, so the adjoint problem, that's why you see the adjoint problem being related to the forward PDE. So depending on your forward PDE, if you have multi-physics coupling, you're going to have different forward PDE.
That's right.
You need to do that. You need to do your adjoint.
Is the lambda t here, is that the Lagrange multiplier? The setup or what?
Yes, correct.
Is that known in the case here, or is it? Because if you go back to the 96, yeah.
Yeah.
Because I see the bilinear operator all the
Oh,
left. I see that one there, and I see this lambda t here. So are you? Oh, you can done a form. Okay, so that's okay. So I see that's how it becomes a linear function.
Yeah. So this is the term from the objective, the forcing difference in objective.
Okay, so you know your multiplier.
So it's just surface.
Oh, the first stress measure.
Surface.
Oh, you're using the attraction boundary condition as your multiplier. At your okay.
Yeah,
I got it.
that's the stipulated attraction, which we then compare it with the.
That's your okay. Your TBC becomes your Lagrange multiplier, So now you have a linear. Okay. Okay. Thank you.
Yeah, thank you for the presentation. So I guess kind of related to this question about how like part of the image to constitutive relation process, if you have to postulate a constitutive law like Mooney-Rivlin or something. So I guess like one of the like constraints that I'm thinking about for that is like you have to know or like postulate the type of material that you're working. And that also it can kind of limit the like for example, if you have strain rate dependence, because you're making your image to constitutive relation like optimization over a single example. And within like kind of presuming that within a single quality static, or even if you have like a higher strain rate test, there's not going to be a large range of strain rates within one experiment. So yeah, I guess is that something you're thinking about how it's like use this process across like experiments with varying strain rates?
Yeah. Yeah, so that's definitely something where you can extend this really straightforwardly to account for multiple different data. So in fact, for plasticity, most of the time you have to consider strain rate dependence, right? So when we test it for plasticity, we now basically see like okay, now you basically have to sum over. So basically you have multiple objectives, right? So you have one single experiment, then you can add more experiments basically. But this is extendable to however many experiments you want to run. And certainly for plasticity, we consider 4 or 5 different experiments at varying rates as well. Yeah. But so the problem and the question I always get when I present on this is you have to assume constitutive form. Right, and that really is difficult. Now, usually we have some idea of the material we start with. So for metals, usually you would postulate some plasticity form, right? But yeah, I mean, in general, you kind of have to know you kind of have to have some knowledge about your material to be able to postulate the model form. You can also try and do basically like machine learning or neural network approximation and just have a hyperparameterized model form and then get your parameters that way. So you can do that as well. And that's something we're also thinking about doing.
Thank you.
Curiosity. So have you tried it with kind of like a machine learning type of, parameter fitting and how did that?
Yeah, we've tried it. It kind of works. It kind of works. It's like any machine learning. Yeah, right. It kind of works. So we have tried it for again the same data set, so the same rubber materials. And then we postulate also instead of like this Mooney-Rivlin model form, we postulate a neural network hyperparameterized model form, and they behave fairly similarly. That's a pretty simple case.
For the hyperparameterized models, how do you ensure that the form you get is going to be like satisfying second law? Or
yeah, you have to encode that in your architecture. Yeah. Which we did, because if you don't, then they actually fail pretty quickly if you do not have that restriction.
For which one?
For machine learning.
Question mark.
Yeah, I think it's a little too unrestricted.
Yeah,
right.
they're freely looking for.
Yeah. So you really try and constrain all these machine learning hyperparameterized model as much as you can from the physics.
But I think again, it's you already know the considered model a priori. Like that's
You're just assuming.
you just like let the learning find a considered model.
Right. What she's asking about is that you just are assuming that the model really has to still satisfy your continuum mechanics.
Sure.
So your thermodynamics.
Yeah.
And so you can import that in.
But enforcing that second law hampers the optimization procedure, like does it create any sort of like unsmoothness kind of the loss landscape that I haven't occurred?
I actually don't know, maybe. But it certainly makes us able to run the inversion problem because if your model is very, very unconstrained, you actually cannot even satisfy your forward P, right? So because it's basically an unphysical model if you are unconstrained.
Any other question?
have you published that paper, the work regarding the, neural network?
We've only published this part, the Harvard. Do people here work on neural networks?
Not that much.
Not
I
that
don't know. Well, I mean, Xiaofan is,
We didn't
but
get.
not for mechanics, not for
Not from
mechanics.
me, I think Google. Yeah.
Google-
Google.
Well, I guess we can continue the discussion with pizza and some coffee, but let's thank Adeline one more. Oh, we have like that small gift as well from Sean, so.
It's not from the USA.
Yeah, for you. Yeah, well, thank you for coming. It was great to have you. Yeah, I know. Yeah, well, I mean, right now it's just like discussion and further questions. Yeah. But feel free to leave if you want to leave, but yeah. Thank you for.